Hello, welcome to today's lesson. So we're still actually on this chapter about linear maps. We're going to go to matrix representation of the maps. Okay, that's the matrix representation. And maybe this is something that you already had the intuition of when we are working in finite dimensional space, as the whole stuff today is going to be in finite dimensional spaces. We will have a matrix representation of our map, whether we are in typical or n spaces, or maybe in some spaces of polynomials which have finite dimension, or spaces of matrices, whatever, as long as we have finite dimension. By the way, while we are here, I wanted to point out two things. What about the pictures that we have here? Look at those pictures. So this one here, well, that represents the idea of the kernel and the image of a map. Okay, you see you've got your map, let's call it, it's called T on that drawing, so let's call that T. That belongs to the set of linear maps between space V and linear space W. Okay, and so the image of V, of the whole V space, it's going to be, so the image of all this, all right, it's going to be, well, that portion of W. It doesn't have to be the whole of W. That's the thing. When the map is not surjective, it's just going to describe just a subspace of W. And so that's about the image. And when we are looking at the kernel, what is the kernel of T? So the kernel is just going to be that subset of the space V that has image precisely equal to 0. Okay, so that can be just more than just one single item. Of course, the image of 0 is going to be 0, but we may have many more items in the kernel, and that's going to be 0. Okay, that was about this picture. About the pictures that we have here on the left-hand side, you've got some matrices that represent some geometric transformations. We're going to go to some geometric transformations that can be represented by matrices, but maybe I haven't talked too much about that. Linear algebra and that part that we are working on, it's really, I mean, the root of many other applications, physical or whatever applications. I mean, it's really something completely basic that you will find use in many areas of physics, like I don't know, some things that come to my mind would be signal processing, image processing, that's sound processing, and also on a completely different subject, cryptography, for instance, whatever. It's really something that is really widely used, and it's the basis of a lot of other applications. Okay, so let's see what comes next. So one of the fundamental consequences of the rank nullity theorem was this corollary, this one here. We've got two finite dimensional spaces, E and F, and we said that they are isomorphic if you can find an isomorphism that goes from one to the other. And of course back, because the idea of isomorphism is that it's invertible. Actually, that's why it is so it's such a nice property. It means that you can take an item from the domain, find the image in the codomain, but you could also go uniquely from any points from the codomain to a point in the domain. You can go to the codomain and back uniquely. That's why it's so important to have isomorphism. For instance, I just talked about cryptography. So the thing is that if you can use, you can transform your message into something else using, I don't know, a linear map, maybe linear is not the most efficient, but let's say it's a linear map, and then you know it's an isomorphism. It means that once you have the coded message, you can decode it uniquely. Okay, that's why it's very important to have isomorphism, and that's why it's a property that we often have a lot of interest in. Okay, okay. So what's said afterward? If you watch the proof of this corollary, and so I invite you to watch again this video because it has a lot of interesting properties. You know, for instance, how to build an isomorphism between or n of x and or n plus 1. So I invite you to pause this video for a few minutes and find an isomorphism that will take items from the set of polynomials of degree at most n into vectors in the space or n plus 1. So pause this video and try to build this isomorphism and come back. Okay, so have you found the isomorphism that could take us from a space of polynomials of degree at most n into or n plus 1? So as we said several times, a linear map is entirely described by the image of a basis of its domain. Okay, so a basis of or n plus 1 is going to be, or n of x is actually spanned by, well, that's the standard basis, 1x, x2, and x to the n. That's the standard basis of Rn of x. And the standard basis of Rn plus 1 of x is just going to be, so or n plus 1, so not of x, or n plus 1, it's just going to be the span of, well, we can take the vectors 1, 0, 0, 0, and then the vector 0, 1, 0, etc. And finally, the last vector would be the vector full of zeros and with a 1 finally. So let's call these vectors E1, E2, En, and it's the vector that has series of n components that has, so Ek as n components, and Ekj is equal to 0 if j is different from k, and 1 if j is equal to k. But this is really the usual Cartesian basis, well, expanded to a space of size. Oh, I said n, it should be n plus 1, of course, En plus 1. So n plus 1 components. Sorry about that. So how do we, why do I need n plus 1? Because obviously I've got n plus 1 items here. I've got 1, the degree 0, degree 1, degree 2, and up to degree n, it's going to be n plus 1 items because I've got degree 0. So to describe this isomorphism, I just have to put, so maybe I should, I can say that I'm going to denote this isomorphism phi, and it just says that phi of x k is going to be mapped into the corresponding, so that's the kth element of the standard basis of Rn of x, and I'm going to map it into the k plus 1's elements, so that should be E k plus 1, k plus 1's element of the standard basis of Rn plus 1. Okay, so that phi of 1 would be equal to the 1, 0, 0, 0. Phi of x would be give you the 0, 1, 0, etc. And phi of x to the n would be the last one. So the vector with n plus 1 component with zeros except on the last item, which is a 1. Okay, so that's just the usual, the most simple isomorphism we can build. And of course, we can build phi minus 1 phi minus 1, which is just going to give you from ek, it's just going to give you you're going to have ek, sorry, ek phi minus 1 of ek is x power k minus 1. Okay, 4k is equal to n plus 1. Well, it starts at 1 and goes up to n plus 1. Okay, so that it goes from x to the n, from 1 to x to the n. Okay, and so the good thing with this kind of representation is that now that I've built this, let's say, very standard isomorphism, I can also represent any polynomial from Rn into a vector from Rn plus 1. So we've got that example where we have this polynomial here. Let's say it's 1 plus 2x plus 3x2 plus 4x3. I can make it a vector of R4, which is just going to be to have 1, 2, 3, and 4 components. Okay, and you can, for instance, remark that if I've got two polynomials, let's say P1 is equal to A1 plus A2x plus A3 x2 plus a4x cubed, and I've got p2 of x, which would be b1 plus b2x plus b3x2 plus b4x 4x3, sorry. You know how to make p1 of x plus p2 of x. You know that it's just going to be the polynomial represented by a1 plus b1 plus a2 plus b2 times x, etc. But you could also use the vector representation and say that p1 is actually the vector, sorry, it's not writing. So P1 could be represented by vector A1, A2, A3, A4. And vector P2 is going to be represented by vector B1, B2, B3, B4. And the sum of those vectors is just, well, as expected when you're summing vectors, A1 plus B1, A2 plus B2, A3 plus b3, a4 plus b4, and this is the also the representation of the vector of the sum of the two polynomials. Okay, so whatever operations you were doing on items of the first set, okay, so in our case it was in our 3 of x, you can do exactly the same representation, the same operations that you can do in a vector space using the vector representation, okay, using the vectors that you have, so that any linear combination of items of the space can be represented as linear combination of the corresponding vectors.